Alright, hello class. Today we're going to be talking about 3.4, which is on trig functions, or trigonometric functions. And here's where things start to actually get interesting when we get way more examples that we can look at. Because previously when we were looking at the product rule and the quotient rule, there wasn't really much that we could do. I mean, we had powers of x and e to the x. That's really all we could play with. Now we're going to start bringing in things like sine, cosine, tangent, and whatnot, and this gives us a wide range of derivatives that we can take. Okay. Now to start this discussion, what we're going to look at first is what I like to call the famous trig limits. Because remember, to look at the derivatives, we will need to look at some limits. And the two famous trig limits we're going to look at is this one. We have the limit as x goes to 0 of sine of x over x is equal to 1. Now, you all saw this on one of your worksheets. One of your limit worksheets. You used a table to show that this was equal to 1. And that's where we're going to leave that explanation for now. The explanation of why sine x over x is equal to 1 is a little complicated. It takes a long time. It's not really worth the time, I think, in class. For those of you who are interested, you can feel free to come talk to me. And I believe there's a proof in your book to show why this is true. The other famous limit, or this one's maybe not as famous, the limit of x going to 0 of sine x over x equal to 1 is very famous. It's a very important limit. It's used a lot. Okay, but this one we'll be using in today's discussion. That's basically saying that the limit as x goes to 0, cosine x minus 1 all over x is 0. Okay. Now, these two are fairly important to today's discussion, but the most important one that you should take away from this is the limit as x goes to 0 of sine x over x is equal to 1. This one, though, cosine x minus 1 over x as x goes to 0 is equal to 0. We can show why that is true. Okay. Note it's a 0 over 0 case. If you go to plug in 0, this is 1 minus 1 over 0, so you get 0 over 0. So you either factor and cancel or use a conjugating factor. That's the strategies we have so far. And actually we use a conjugating factor for this one. I'll have the limit as x goes to 0 of cosine x minus 1 over x. And I'm going to multiply by cosine x plus 1 on the top and on the bottom. Okay. Use that conjugating factor. We looked at an example of this back in the earlier limit sections. And we basically multiply this through. When you FOIL out the top, right, we're going to end up getting the first term squared, so cosine squared, minus the second term squared, which is just 1. Okay. And this is all over x times cosine x plus 1. All right, and you might be thinking, well, now what do we do? Right? This hasn't really simplified anything. But we're going to start using identities. All right, and the most important trig identity we have is that sine squared x plus cosine squared x is equal to 1. And that isn't exactly what we have here, but if we start moving things around, say if I move the 1 over to this side and the sine squared x over to this side, we would get cosine squared x minus 1 is equal to negative sine squared x. Right? So that gives us that this limit is technically equal to the limit as x goes to 0 of negative sine squared x all over x times cosine x plus 1. Right? Now, you might think, well, that didn't really help. But it does if we start splitting things up. So what I'm going to do, I have two signs on the top, so I'm going to break that apart and move one of them to be over the x and the other one to just be over this cosine x plus 1. Here, I'll show you what I mean. We basically have the limit as x goes to 0 of negative sine x over x times sine x over cosine x plus 1. Right? Now, from here, the limit is sine x over x as x goes to 0. That's our famous trig limit. That's equal to 1. So this thing here, right, is going to 1, and specifically negative 1. And now we have this limit piece. As x goes to 0, the top here is going to 0, and the bottom, cosine of 0, is 1. So this whole thing is going to be 2. So the whole limit comes out to be equal to negative 1, that's the first piece, times 0 over 2. And we plug everything in. And this whole thing comes out to be 0. Right? Let me write that up there like that, which is what we got here. Like cosine of x minus 1 all over x, we take the limit of that as x goes to 0, we get 0. Okay. Now your book is actually going to be asking you to do some problems, and you'll actually have a worksheet that asks you to do this and using, or basically doing limit problems involving sine x over x. So let's look at a couple of examples that deal with that. Okay, so let's start with the limit as x goes to 0 of sine x times cosine x all over x. Okay. To do this one, we do it much like the one we just did, where we break things up. So that's what a lot of these end up being, is we break things up. Okay. So here, and we do that because we want to get the sine x over x isolated, right? If we can get sine x over x all by itself isolated, then that means we know that piece is equal to 1. So in this case, if I rewrite this, if I break that cosine off of the fraction, I'll get the limit as x goes to 0 of sine x over x times cosine x. Okay, and now I know this entire piece here is going to 1, since it's the limit as x goes to 0 of sine x over x. So that goes to 1. Then cosine x, well, now we can just evaluate the limit, because this will be 1 times cosine of 0. We'll plug 0 in, and cosine of 0 is 1, so the whole thing comes out to be 1. Like that. Not too bad. Another example where we would break pieces off. Let's say I have the limit as x goes to 0 of 2 sine cubed x all over x squared. Okay, so whenever you see something like this, sine cubed x, sine squared x, what you're basically going to do is just break it up into 3 pieces, right? How many sines do I have in this example? Well, I've got 3. All right, I've got sine x times sine x times sine x. And then underneath I have x squared, so I actually have 2 x's. So when I do the fraction, I have an x and an x. So I'm going to let one of these x's hit one of those signs, and another x hit another one of these signs. So basically what I have when I break all this up is I have 2 times sine x over x times sine x over x times sine of x. Okay? Remember, sine has to have an input, an x. You can't just say sine. Okay? So now what I've done is I've broken it down to where I've isolated all the sine x over x's, and this piece goes to 1, this piece goes to 1, and now what I have is 2 times 1 times 1 times sine of 0. We can just plug the x value in, and this actually ends up being 0. All right, and the final example type would be something like this. If I wanted the limit as x goes to 0 of sine of 2x all over x. Now this one, right, for this to work, now a lot of you, I mean, you probably noticed something just like this on your test where you're using a table, and you probably saw either sine of 3x or sine of 4x. You might have had sine of 2x, I don't really remember. But what you got was sine of like 3x over x as x goes to 0 was 3. If you had a 4 there, you probably saw 4. Okay. So here's how this works. For this to work, I need the variable on the inside to match the variable on the bottom. All right, we have sine of x over x, and these two things have to match, right? So if I put a 2 in here, I'd have to put a 2 down here. So I'm going to put a 2 down here, but I can't just put a 2 on the bottom, right? I'm going to have to put it on the top and the bottom. So in some of these problems, you'll actually have to multiply the top and the bottom by a number so that you get the limit as x goes to 0 of 2 sine of 2x over 2x. And now we have matching variable inside sine and beneath sine. So this piece goes to 1, leaving the limit to be 2 times 1. All right, so that's really how you use this famous trig limit in, say, math problems that your book might give you. Now we're going to actually use it to try and figure out what the derivative of sine is, and we'll see both of these famous limits come about. Okay. Another thing we will actually need for finding the derivative of sine is this trig identity here, which says sine, if you have theta plus phi, okay, that breaks down into sine of theta plus sine of, sine of theta cosine of phi plus sine of phi cosine theta. Okay, this is the sum identity. There's sum and difference identities for trig functions, and we will actually need this identity to figure out the derivative of sine. So let's start here. I'm going to let f of x be sine of x, and we're going to find f prime of x. So f prime of x is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h. So what this really is the limit as h goes to 0 of sine of x plus h minus sine of x all over h. Okay? Now here's where we're going to use this identity. We have the sine of x plus h. I'm going to break that up with this identity. Right, so this is sine x times cosine of h plus sine of h times cosine of x minus sine of x, all over h. I'm going off the view here. So what we're going to do from here, right, you might think I just made things worse, but I'm actually going to join some pieces together. I have this sine x cosine h minus sine x, so I have two sine x pieces, and then I have this sine h cosine x piece. So let's move the pieces with sine x together. Okay. So I'll get the limit as h goes to 0 of sine x cosine h minus sine x, okay, plus sine h cosine x. And I have went ahead and broke up this fraction. Okay. Now the reason is, take a look at this piece. Here is sine h over h as h goes to 0. This is eventually going to go to 1. And then, well, we almost have that other limit, right? If I factor out a sine in this piece, I'd have cosine h minus 1. And I guess I should be careful about that, because that's not hyperbolic cosine, for those of you who know what that is. I'll have the cosine h minus 1 all over h as h goes to 0, which is our other special limit, right? So this comes out to be the limit as h goes to 0. I factor out the sine completely in this piece, so I have sine of x times cosine h minus 1 all over h. Right? And then I will rewrite this piece so that it's sine h over h times cosine x. Okay. Now if we go back to our special limits here, we know sine of x over x as x goes to 0 is 1. Well, here we have sine h over h as h goes to 0, so this piece is going to 1. And then I know cosine x minus 1 over x as x goes to 0 is 0. So here we have cosine h minus 1 over h as h goes to 0. So this whole thing goes to 0. Okay, so in the next step, we get this is sine x times 0. I'm just writing it out. Plus 1 times cosine x. Of course, this comes out to be cosine of x. So what we have found is that the derivative with respect to x of sine of x is cosine of x. So the derivative of sine is cosine. That's a very interesting result, I think, that when you take the derivative of one trig function, you get the co-function. Okay. Now, the derivative with respect to x of cosine, well, you could do all this work over again. Same exact work, using a similar identity for cosine, using the same special limits and all that. But you go through all that work all over again, and you basically get that cosine x is equal to negative sine of x when you take the derivative. Okay, so the derivative of sine is equal to cosine x, and the derivative of cosine is equal to negative sine x. Okay, so from here, we can find the derivative of all the other trig functions without having to use the limit definition. Okay, so the derivative of tangent, for example, let's say I want to take the derivative of tangent of x. Well, the derivative of tangent, well, tangent I can rewrite as sine of x over cosine x. And I should put my derivative sign in there. Right, so basically if I'm taking the derivative of tangent, I'm taking the derivative of sine of x over cosine x. And I can take the derivative of this using the quotient rule, right? So the quotient rule says that this will be the derivative of the top, so the derivative of sine x, I'll write it out very explicitly, okay, times the bottom left alone, minus the top left alone, times the derivative of the bottom, all over the bottom squared. So this ends up being the derivative of sine we found was cosine. So we have cosine times cosine, so we get cosine squared. Okay, minus we have sine x times the derivative of cosine, which we found was negative sine x. Still all over cosine squared. And so negative sine times negative sine, that's going to give us, do it down here, cosine squared x plus sine squared x over cosine squared x. And cosine squared x plus sine squared x is 1. So this is 1 over cosine squared x. And that could be our rule for the derivative of tangent, but instead what we're going to say is that, well, 1 over cosine is actually secant. Right, so this ends up being secant squared x. Right, so that's the derivative of tangent. So the derivative of tangent, let me put it on this page here. The derivative of tangent we just found is secant squared x. And if you go through all that work again, using the quotient rule and everything, starting with cotangent, right, because cotangent of x is cosine over sine, you actually end up getting negative cosecant squared. Okay, so that is the derivative of tangent and cotangent. And an interesting thing about these derivative rules for trig functions, the derivative of tangent is secant squared, the derivative of cotangent is pretty much exactly the same, right? Except you negate it and you change it to the cofunction, right? So the derivative of tangent is secant squared, but the derivative of cotangent will be, you negate it and change it. So it would be negative cosecant squared x. All right, let's now look at the derivative of secant. All right, we got some secants in here. So the derivative of secant well, we're going to do a similar process. All right, this is the derivative of 1 over cosine of x. Okay. And we're going to use the quotient rule again. Right, so it will be the derivative of the top, which is 0, times the bottom left alone, minus the top left alone, times the derivative of the bottom, which will be negative sine x, all over the bottom squared, which will be cosine squared x. Okay. So simplifying this out, this whole piece goes to 0, and so we have sine x over cosine squared x. Now, we could leave it like this, but again, you look this property up in any book, it's not going to say sine x over cosine squared x. What it does instead is it breaks this fraction up, right? So it breaks this up like so. It breaks it up as 1 over cosine x times sine x over cosine x. All right, because we essentially have a 1 times sine and a cosine times cosine. So you break up the fraction, and this is secant, and this is tangent. So the derivative of secant x is secant x times tangent x. Okay, so that's the rule for secant. So the derivative with respect to x of secant x is secant x tangent x. And the derivative of cosecant, if we were to follow the same pattern that we've been seeing before, right? Well, if you were to guess that it followed the same property as before, that we would negate it and change those functions to co-functions, you'd be absolutely right. If you went through that work again, you would get the derivative of cosecant x is negative cosecant x times cotangent x. Okay. That finishes off our trig derivatives. Okay, so let's write them again all in one go so we can take a look at them before we start doing a bunch of examples. Okay, so here are the 6 trig derivatives. All right, derivative of sine is cosine, derivative of cosine is negative sine. Right? The derivative of tangent is secant squared x. Derivative of cotangent is negative cosecant squared x. Derivative of secant x is secant x tangent x. Derivative of cosecant x is negative cosecant x cotangent x. And pretty much, you need to know, of course, that sine x, its derivative is cosine, derivative of cosine is sine. But from there, as long as you just know that the derivative of tangent is secant squared, and the derivative of secant is secant tangent, you have the cotangent and cosecant derivatives right there, because all you do is it's the same pattern, but instead of secant squared, it's negative cosecant squared. Instead of secant x tangent x, it's negative cosecant x cotangent x. Right? You negate and change to a co-function. And essentially that's what you're doing here, right? Derivative of sine is cosine, but then the derivative of cosine is where you negate it and change the co-function back to a normal sign. Okay. So those are our 6 trig derivatives that we'll be utilizing. All right, so let's look at some examples. All right, we'll start with something like this. Let's say we have y is equal to 2x to the 7th plus tangent x minus cosine x plus sine of 2. Okay? And so we're just kind of mixing this in with types of problems we've looked at before. So let's say, well, we'll take dy for dx, 2x to the 7th. Hopefully by now you know that that's 14x to the 6th. Plus, what's the derivative of tangent? Well, go ahead and tell me what it would be. Of course, I can't hear you, but that's right. It's going to be secant squared x. Okay. Minus, now what's the derivative of cosine? It's negative sine x. Now, of course, you don't have to write this step, but be careful. If you have negative cosine, you'll end up getting a positive sine. And then what about sine of 2? Well, sine of 2 is just a constant, so that comes out to be 0, of course. So our answer is 14x to the 6th plus secant squared x plus sine x. And we're finished. Okay, how about this function? Say I have f of x is equal to e to the x over 5 plus cotangent x minus 3 cosecant x plus 9 sine of x. So I kind of ended with the easiest one there. So f prime of x, well, we've seen this enough times. E to the x over 5, that's e to the 1/5 x. Right, so this will be 1/5 e to the x over 5. Okay. Plus, that constant comes along for the ride, and then the derivative of cotangent x is negative cosecant squared x. Okay. Then I have negative 3 times the derivative of cosecant x, which is, well, how about you should be able to tell me. Again, can't hear you, but go ahead and make a guess of what that would be. And yeah, that's negative cosecant x cotangent x. And then plus 9. What's the derivative of sine? Of course, is cosine. Okay, so we can simplify some of this stuff. This is 1/5 e to the x over 5 minus 15 cosecant squared x plus 3 cosecant x cotangent x plus 9 cosine x. All right, fair enough. Okay. We can also start bringing sines and cosines and whatnot, trig functions, into products and quotient rules. Let's start with a simple one. Let's say we have x squared cosine x. Okay, when I take the derivative, well, it'll be the derivative of the first. First guy is x squared, so that will be 2x times, oh, that didn't help, times the second guy left alone, okay, plus the first guy left alone times the derivative of the second guy, which would be negative sine of x. So to finish this off, this is basically just 2x cosine x minus x squared sine x. Okay, and that is that. Okay, let's say I want to find the derivative of sine squared x. Now, this is much easier if we have the chain rule, but unfortunately we don't. So since all we have are our basic trig rules and other things like that, we're actually going to have to use the product rule here, because this is actually sine x times sine x. Okay, so this will actually be a product rule. So when we take the derivative, it will be the derivative of the first, which is cosine x, okay, times the second guy left alone, plus the first guy left alone, times the derivative of the second guy, which ends up being cosine x. Okay. So I have cosine x sine x plus sine x cosine x. You can write that however either way. I'm going to reverse this one and make this sine x cosine x. Right? So we basically have 2 sine x cosine x. Okay, and that's that. We can continue this idea. Let's say I start with f of x equals secant x tangent x. Now you might think that looks familiar, right? That's the derivative of secant. So essentially this is like taking the second derivative of secant. Okay? So now we're going to take the derivative of secant x tangent x, and that's also going to be a product rule. Okay? So when I take the derivative, it will be the derivative of the first, which I will put in parentheses. The first function is secant. What's the derivative of secant? It is secant x tangent x. Okay, so there's the derivative of that guy. Then it will be the second function left alone, okay, plus, okay, now the first function left alone. Now in parentheses I'm putting the derivative of the second function. So the derivative of the second function, derivative of tangent, is secant squared x. Okay. And there we go. Now we have this function here that we can actually simplify. You could say, a lot of ways you could simplify this. You could say this is secant tangent squared x plus secant cubed x. Right, that's one way to do it. So secant x tangent squared x plus secant cubed x. And that's good enough. You could also factor out a secant, but I don't know if that makes it much easier. You could say secant x all times tangent squared x plus secant squared x. Okay, and there's that one done. Okay, next example, we have 3x plus 1 times sine x all over sine x plus 2. This, of course, is a quotient rule, but we have a product rule in the top. So this will be quotient rule with product in the top. Okay, so I always think it's a good idea to make a note to yourself of what rule you're going to use. Right? Tell yourself, right, this is a quotient rule, but I have a product rule in the top. Right? So when you go to do the first step of the quotient rule, which is the derivative of the top, you know that that's going to be a product rule. Right? So in brackets, we'll put the derivative of the top, which will be a quotient rule. So derivative of 3x plus 1, well, it will be the derivative of the first, which is just 3, times the second guy left alone, plus the first guy left alone, times the derivative of the second guy, which is cosine x. Alright, this whole thing here is the derivative of the top. Let me write that in a different color. You got the derivative of the top. Then the next piece is the bottom left alone. So that will be sine x plus 2. Right. And then it will be the top left alone, which will be 3x plus 1 times sine x, and I'm definitely running out of room. And then in brackets here, I will put the derivative of the bottom. And the derivative of the bottom, well, the derivative of the bottom sine x plus 2. So that will end up being cosine x. Almost didn't make it on this paper. Okay. Here I can actually make this fit a little better. Sine x, cosine x. There we go. Okay. And the whole thing, so here, remember this is the derivative here of the bottom. And then with the quotient rule, the next thing you do is put it all over the bottom squared. And I made a mistake here. What did I do? This is supposed to be a minus sign. Sorry about that. It's a minus. Okay. And honestly, I would pretty much just leave it like this. I think the only real thing you could do to simplify that would drop the parentheses on this 3 here. And yeah, I wouldn't simplify that any further. Okay, I would just move on from here. All right, so how about for our next example, we look at y equals tangent of t all over 1 minus secant of t. So when I take the derivative here, it will be dy over dt. That's the variable we're using. Right? So from here, this is going to be a quotient rule. Right? So it will be the derivative of the top, and the derivative of the top, well, the derivative of tangent is secant squared. Right? Then times the bottom left alone. Right? Minus, okay, the top left alone, times the derivative of the bottom. So the bottom is 1 minus secant t, and the derivative of secant t is negative secant t tangent t. Now, here you have to be very careful about your parentheses. You have to put parentheses here to say that you're multiplying by a negative. Otherwise, it will look like you're subtracting. Okay? And before you ask, that is something I would take off for because, you know, the algebra would be incorrect. Okay, it's time to start being very careful with your parentheses, although a wavy fraction sign is okay. Now, this whole thing goes over 1 minus secant t, the bottom, squared. And we're pretty much finished, although, you know, you may want to simplify this a bit. In fact, if I were doing this, I would actually say that this is equal to, I'd leave the first thing alone, right? I wouldn't really simplify that much. But what I would do, okay, is change this to a plus, since I have a minus minus, and then say that this is secant t tangent squared t all over 1 minus secant t squared. Okay, that just looks a lot better. Right. And you know, you could factor out a secant and do some other things, but I think this is fine right here. All right. Okay, let's look at another example. All right, next example, we have y is equal to 1 plus cosecant of x all over cotangent of x. Right, so this is going to be quotient rule. So, have dy over dx is going to be, so remember, top goes first, so the derivative of the top, well, the 1, that'll go to 0, and then I have the derivative of cosecant, which will be negative cosecant x cotangent x. Right, so there's the derivative of the top. Then it's times the bottom left alone. So I'm going to write this out just so it's clear what everything is. This is derivative with respect to x of the top. Here's the bottom left alone. Okay. It'll be minus. Right, now the top left alone times the derivative of the bottom, and the bottom derivative of cotangent, go ahead and write down what you think that would be. Okay. And if you put negative cosecant squared, you are absolutely right. Now, what a lot of people do is when they notice that this negative piece is, or the second piece is going to be negative, they'll go ahead and make that positive. Right? So you'll probably see me start doing that from now on. Oh, that's going to be negative. Let me just make that positive as part of the process. So this here is the top left alone, and here's the derivative of the bottom. Okay, and then all over the bottom squared, that will be cotangent squared x. And as far as I would simplify this, it'd be negative cosecant x cotangent squared x minus, and we have, actually I'd make that a plus, 1 plus cosecant x times cosecant squared x all over cotangent squared x. And you could do a lot of simplifications here, do a lot of trig manipulation, probably get this down to look like something really nice, but we're not going to do that. Okay, for this, at least now, right? For this, I just want you to take the derivative, move on. You don't want to waste a lot of time. You might want to, you know, be really careful, simplify things so that your signs are correct and all that. But other than that, I mean, just move on. All right, that's about all I really want to talk about in terms of trig functions. There's many more examples to do, and you all will do a lot to practice in class, many examples and whatnot, but if you remember these rules, you should be all right, and get them down really well, because once we move on to the chain rule, which will be the next section, if you don't have these basic derivative rules down, you might just think, oh, these are easy, no big deal, you know, no problem, whatever. But if you don't have them down really, really well, okay? If you don't really practice them and get them down, once we hit the chain rule, you're going to have a really hard time if you don't have those basic rules down. Okay, so make sure you have these 6 down, and really you only need sine and cosine, tangent and secant, because if you have a cotangent and a cosecant, you know, it's the same thing, you just negate it and change it to the cofunction. All right, what I want to talk about in the, you know, the final little bit of this lecture is actually section 3.5, and I'm not going to spend much time with this because this section we've already talked about a lot. Actually, the whole section is on derivatives as rates of change, and honestly we've really been talking about that already, right? That the derivative of a function is its rate of change. And so, for example, if we had our position function, which is s of t, and we take the derivative, what do we get out? Well, we get the velocity, p of t, which is the rate of change of the position, right? So rate of change of s, that's what that gives us. Hopefully you understand what I mean there. And then if we were to take the derivative of the velocity, right, we get acceleration, a of t, or, well, we'll use lowercase a, not that it matters all that much. We get a of t, and this is the rate of change of v. Okay. But what 3.5 starts to really look at is that it doesn't have to be position, velocity, acceleration. It can be all sorts of things. It could be how, say, demand is changing in an economics problem. It could be how the population changes over time. If you have a population of bacteria or you have a population of people over time, how the population changes. And so the derivative, if you have a function that gives you the population, then the derivative would give you the rate of change of the population. So, for example, I'll just ignore this for now. Say I have p of t gives the population, right, over t years. When we take the derivative, right, p prime of t, well, this is the rate of change given in population. So let's say this was people, okay? Okay, so this would be people per year. All right? Whenever you look at units of a derivative, it will always be something for something else. It could be the amount of money in your account, right? So a of t could be money in your interest-bearing account. And if we took the derivative with respect to t, we'd get a prime of t, which will be, of course, the rate of change. But this would be in dollars per year, if this was in t years. Okay, it could be in months or whatever. Okay, so let's look at an example where it's not position and velocity, it's something else. Okay, so let's say that the volume of water in a tank at t hours is given by this function here, v of t equals t squared minus 20t plus 100. So this is giving us the volume of water in gallons at t hours. Okay, and so we want to find and interpret v prime of t at t equals 0, t equals 5, t equals 10, and t equals 15 hours. Okay, and see what's going on. All right. So first thing I want to mention is that if we plug in 0 here to give the initial volume, all right, this isn't answering this question yet. Okay, I'm just saying if I were to plug in 0, I would get 100. So the tank starts out at a volume of 100 gallons. Okay? Just to kind of give you a rough idea of where we're starting. Now, when I take the derivative, we start with something simple here. Derivative of capital V will be 2t minus 20, and that 100 disappears. So from here, we can start plugging in the values. So V prime of 0, plug in 0, I will get negative 20. And negative 20 what? Well, it's always going to be the units of your function divided by the units of your independent variable. So here it's going to be the units. So I'll write this over here. It will always be the units of your dependent variable over the units of your independent variable. So it's going to be gallons per hour. All right, and what's happening is we're either filling up the tank or we're emptying the tank. One of those things is happening. And what I have here is that at t equals 0, I have a rate of negative 20 gallons per hour. What do you think that means? Okay. What does the negative 20 mean? Well, this means that initially at t equals 0, we're emptying the tank. At, well, 20 gallons per hour. Okay. So when you empty the tank at 20 gallons per hour, and that's only at t equals 0, right? That doesn't mean it's a constant rate. It might be speeding up, it might be slowing down, and in fact, what we find when we plug in 1, or sorry, we're not looking at 1, when we plug in 5, so at 5 hours, we get 10 minus 20, so we end up getting negative 10 gallons per hour. So we're still emptying the tank, but we're emptying at a slower rate, right? The rate at which it's emptying is slower. So still emptying, but at a slower rate. At a slower rate of 10, or it's negative 10, but we're emptying at 10 gallons per hour, right? Slowing down. And then what happens at t equals 10? At the 10-hour mark, plug that in, you get 0 gallons per hour. That means we've stopped, right? We've emptied the tank, and we've stopped emptying. Or, sorry, we've been emptying the tank. I don't know if we've actually emptied it yet, but we've been emptying the tank. Maybe now we slowly, maybe we're closing the gate or whatever it is, very, very slowly. It took 10 hours to do it, but we finally closed that gate off or whatever, and so we've stopped emptying the tank. So here's we've stopped emptying the tank. And then what happens at v prime of 15? Well, we would get 30 minus 20, so that is going to be 10 gallons per hour. So now we are actually filling up this tank at 10 gallons per hour. Okay? And so, say we started off by emptying the tank, and at 10 hours we stopped, but by 15 hours we've started filling it back up again. And in fact, if you look at what the graph of this original function looks like, okay, if this is 100, so this is our volume, V, here's, let's say, the 10-hour mark, and this graph looks like this. So essentially initially we have 100 gallons but the volume starts decreasing, so the tank is emptying, and then at the 10-hour mark, that's when the tank is actually empty. Right? If we go back to the formula, if you put in 10 into here, right, you'll get 100 plus 100 minus 200. That's 0. That's when the tank is empty. So that's why we had to stop emptying it, right? There's nothing left. And then right at that point, we start filling the tank back up again until we hit this is the 20-hour mark. We will be back up to 100 gallons again. Okay? Now here's the thing about this stuff. I can't go through every single type of example you will ever see. It's impossible, right? I can show you how we think about it though, all right? And always, 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 if you're looking at the derivative f prime is going to always be in units of f over units of x. And that's how you can interpret it. And if you get a positive rate, that means f is increasing, whatever that might mean. You're going to have to think about this, right? You're going to have to use your brain and actually think that if I was talking about volume of water in a tank, and I get a negative rate, well, that means the volume is decreasing. That means the tank must be emptying. Okay? If I have a population of people, and I look at the derivative, and the derivative is in people per year, and I get a negative rate, that means the population is decaying, it's decreasing. Okay? If I have money in my account, and the rate is in dollars per year, let's say, and I get a negative rate, that means within that year, at that year, the money in my account is decreasing. I'm losing money. Okay? You're going to have to get used to taking this mathematical idea of a negative rate, a positive rate, and translating it in what it means in English. And again, I cannot go through every type of example, but as long as you remember this, that f prime is going to be units of f over units of x, always. Okay? It's a rate. Then you shouldn't have any problem, right? It may, some of them are a little difficult to try and kind of translate your way through, but quite honestly, as long as you have this, it's really nothing to it. Okay, a lot of people like to freak out when they see word problems, but remember, most of the problems in chapter 3 are going to be asking you to find the derivative and asking you questions about it. So if your first step on a lot of these problems is take the derivative, it's probably it. And then if you remember when you try to interpret these things that it's going to be in units of f over units of x, you're pretty much almost all the way there. Okay, so I'll end this now, and so next time we will be talking about the chain rule, unlikely, but cheers.